Okay, now we are going to begin our analysis or our construction of the Bellman-Ford algorithm. And we'll start off with discussing what the shortest path is in terms of the number of hops. Okay, so the primary idea behind the Bellman-Ford algorithm is, can we compute the shortest path from S to C, S to T recursively? Okay, what are the smaller problems from a shortest path of length n? How do we reduce it to a shortest path problem of length n minus 1? So here's the idea. Here's a thought. Let's go back and say, if we have a shortest path, and let G be a directed graph with arbitrary edge lengths, could be negative. If there is a shortest path from S to VK, then for some prefix of this shortest path, that is also a shortest path from S to VI, right? Just because there are negative edge lengths doesn't negate this fundamental property of shortest path, which is that you can't shortcut the shortest path, right? So if you know you have a shortest path to VK, then the shortest path to any intermediate nodes, that also has to be the shortest path to that node. So what do we do with that information? Well, maybe we could calculate the shortest paths with the fewer hops and edges. Maybe we could start off and calculate the shortest paths that only use one edge, then calculate the shortest paths that use two edges, and then calculate the shortest paths that use three edges, and work our way up. All right? Maybe that's how we could formulate this problem recursively. So let's come up with a recursive function called dv of k, which represents the shortest walk length from S to V using at most k edges. Okay, so we say that the distance from S to V is equal to dv comma n minus 1, i.e. the maximum number of edges that you can take for a shortest path is n minus 1, a shortest simple path. Otherwise, you would have a cycle somewhere. So this is the maximum number of edges you could take for a shortest path, and this is the endpoint. And implicit in this function is that you are starting at node S. Okay, so we have a function dv of k that represents the walk length from S to V using at most k edges. So how do we write out the logic? Well, we know dv of k, the shortest path, is either the minimum of dv of k minus 1. Maybe we don't need k edges. Maybe the shortest path is can be accomplished using k minus 1 edges. That's one possibility. We don't need a kth edge. Or the other possibility is that we do need a kth edge. So what happens if we need a kth edge? Then we simply calculate the distance using k minus 1 edges to some arbitrary vertex. And then we add in the weight of that vertex u to v. Okay, so either we're not adding a kth edge or we are adding a kth edge, and there will be some intermediate u for which we took k minus 1 edges to get to u, and then we took the kth edge to get to v. Okay, and of course we need a base case somewhere to start from, and so our base case will simply be that the shortest path from the start node using 0 edges is 0. That's true, right? You don't need any edges to get to the start node from the start node. And we also will start off with a base condition of we assign the shortest distance to all the other vertices using no edges as infinite. Right? Again, you can't use any edges, then you can't reach the other vertices. Okay? So let's do the calculation on a sample graph. let's start off at S, base case. You use 0 edges, and so the distance to S is 0. The distance to other vertices is infinite. And next, we'll say what are the shortest paths to other nodes using at most one edge. So we could look at all the edges. We could calculate all of them for every single edge. And we calculate that the distance using one edge here is 0. Starting from S is 0 plus 6. So we assign 6 to A. We know that the shortest path using one edge is 0 plus 4. So we assign 4 to B. We know that for using one edge, we could get to C by using 0 plus 3, edge length 3. So we assign 3 to C. Okay? Next, let's look at 2 edges. If we need 2 edges, what do? We just recompute the function again, right? We don't necessarily care what the values are. We just simply recompute the function. And so what is the function? The function, so let's go. The distance to get to B. The distance to get to B is the minimum value. I'm going to highlight this. Is either the minimum value of d of k minus 1, i.e. b1, db1, or it's d of some intermediate vertex, some vertex u in v, view using 1 plus the length of edge u, of edge u to b. Okay, so we go through all the other vertices, and in fact we find that there is an edge right here. That if u is equal to c, then we simply take, this is this condition, then we simply take L, which is -1 here, plus u of 1. What is C1? C1 is 3. Okay? So in this case, we get 3 plus -1, which equals 2. So that's why this value changes to 2. Make sense? So we could do similar things. For instance, the distance to get to D using at most 2 edges, what is it? It's here, right? Or another way to put it, it is the minimum for some u in V to the minimum for some u in V for the distance of u1 plus the edge length of u comma d. Okay, so if u is equal to b, then db1 is equal to 4 plus the length of bd, which is equal to 0, so that's equal to 4. Okay, and so we could assign a shortest edge length of 4, which is smaller than infinite. Okay, so we do this practice, we carry out this practice over and over again. We carry out this practice and see that, for instance, if we go to 3 edges, then the shortest distance from S to A goes from 6 to 1. And why is that? Well, it's because we could take this path here, 4, 0, -3. And that is the shortest path to A using at most 3 edges. And we also see that when we finally go up to 3 edges, we could have a distance from S to E, which is using this path. Okay, so for every calculation here, we are looking at all the other vertices of that calculation. We are looking at all the other vertices, and we're looking at the previous value. and taking the min of all of that, the minimum value. And so if we carry out this computation again, we see that the minimum distance to A changes again to -1 because 1, 2, 3, 4. Okay, and we keep going until we settle down, and this gives us the minimum path from S to all other nodes, the minimum path tree. Okay, so that's how the the Bellman-Ford algorithm. Sorry, that's how the Bellman-Ford algorithm works. And in the next section, we're going to discuss its running time and look at its code.